search whatever there is the tag Chicago 14A, you just put whatever you want. So okay. If you want to have a shortcut for your problem, you can define the name here. Let's say the shortcut is TrueView5P, and the default formulation is going to be the TrueV5P 9A formulation. Okay. So when I can use it, I just use this name. I don't need to have that. Okay. Next, let's see whatever we have here. Parameters is the first thing. So you create one for or no problem. I just fill this stuff. Right, so the formulation we have at the moment that we want to explore, from what I see, does it have 40 solutions or does it have 160 solutions? That's what I have to take a look at. I think it has 160 solutions. Right, so now just look that up. Yeah, so the 40 is like real ones. So the average 40 real solutions. So the actually that we have actually have 160 for this, which is really big. This is one concern I have. This small problem shouldn't have that many solutions. So anyways, this formulation uses that. It's already working Julia. So just implementing here. So this is the n, which is the number of variables and equations, 9. Number of parameters, so how do you represent the images in the homotopy? So how many parameters it's gonna be representing. So I have to check that inside Hongis code. Okay, so I'll mark with XXX. From Julia. Okay, so this is from what the representation we had for the visible line representation from the CVPR paper, CVPR 2020. So that's how it worked. You had the representation for the points, the lines, and then this chart is you have to represent the solutions as well. So here, I think we have 10 depths, right? So we have 10 depths, and that's what we write. So I don't know how you're gonna write the image one. So you can think about that later on. Okay, so I'll mark with this everywhere that we should be changing. Now this guy, number of views, 2 views, number of points, 5 points, number of free lines, 0, number of tangents, 0, right? And this number of visible lines, I don't need that. But it's computing here as well. It's already going to compute the number of. This is not important. Anyways, this is not important. So for this formulation, what matters is this guy. Right. So now we coded the problem. Now minus, I just keep going here, see whatever it has Chicago, right? So it has here. So far this is all generic code. This is all generic code. Right, so this is all the parameters for the homotopy if you want to set it up, right? So here's like this. I don't know why the maximum number of iterations is not here. Should have max steps here. I have to check that. Oh yeah, so let me merge this just real quick before we continue. So we're here in Cleveland, so I have to merge master to have that. So okay, so this is the update I had for last meeting. So we now have this max number of steps. I just put 1,000, which works for Chicago, with such a huge problem, so it should work here. I think this problem should require a lot less steps, probably 100 steps you can do it. And so these are the default parameters. These are good parameters from Anton's original code, which is amazingly good. So we had some optimizations for some of these parameters based on our previous paper. So you should really use this. So we optimize some of this that makes it run a lot faster. Okay, so we have this. This is also generic for your problem. You don't need to change any of this. If you want to have a default for your problem, you can have a default set on another header. But for now, all problems have the same default. Then you go here, you have minus IO common. So these are just for generic stuff as well. For IO, right? So all of this is generic. So the only problem specific thing is here, problem defs. So you should copy something like this to your problem. So we have Cleveland here, right? So just copy this. So you just put here, you can put 2 view 5.9a. Okay, so then this is the functions that the specific minus is going to have for that. It's going to have minus core, which is a tracker, IO functions, problem parameters, which we already defined, and then it's going to have 2 solve functions. So the solve functions for this one, so this is what changes from problem to problem. Here you only have points, you don't have tangents, so you can delete this. You don't have tangents, delete. This one is for calibrated, so you have the K matrix. This is uncalibrated. This is when you have the K matrix and your measurements are in pixels. Here's when you have normalized measurements. Now we have the solutions is correct. So this is like 3x4 matrix, right? This is fine. And this is also correct. So that's it, we got it. So all the declarations are in place. Now let's see the implementation. So implementation is always minus.hxx. Minus.hxx. So the implementation, just search for something like Chicago. Right, so should copy whatever we have. So here we have this. So just create another one here. Actually, have some other problems here. We can have true view, 5-point algorithm, and a. Right, so then we implement that. Just copy. Five to view 5-point. So then we get inside of that, and then you see we change everything that you have for Chicago 14A to V 5P array. There we go. Right, so that's it. Just did it step by step so we can have a look at the file. Now, what we do, so we have that. So now I try to search for whatever you have to change. So see, this is the eval function. So this you have to. I'm gonna leave Chicago for now. The implementation for Chicago. So this one you have to fill in. So I'll just leave. Okay. So this is the evaluation for the homotopy, the derivative in x and t. This derivative of x. And it's going to compute these guys. So I'll teach you how to fill this in Macaulay 2. So the first thing we should do is implement in Macaulay 2. Whatever Hongi has in, whatever you have in Julia or some other type of black box solver, you should just follow the steps, put it inside Macaulay 2. Macaulay 2 has a function that does this automatically, this part. Okay. Next. Next thing, you should fill this. So we are in this line 7025. So we should see this file. So we should copy that. Right. So let's go there and let's change again everything that's Chicago for the new problem name. I'm not gonna change this for now, but here's where you have to put your functions to convert whatever input you have to the homotopy input. Then we continue here. We have this is also, so this is the implementation, right? So .age is like it's just the declaration of the functions for I/O, and then the implementation is right here, right next. So this would be like -io.hxx, but it's all inside the same header here. Didn't want to create another header, so you just look at this function. We probably don't need this one, right? So but let's just leave it as a stub. Right, so you just have to delete that. Then you have gamify, which is the randomizer for the input. So this has to be implemented. Okay, so I know how to do this for the visible line implementation. Now for the homotopy implementation is not so clear for the Julia implementation. So if you use different parameters, you have different ways of randomizing it. So you have to think about that. Unless you just use whatever is in Macaulay 2, unless you do some kind of visible line. So this kind of like something you have to figure out how is it done in Julia, and you have to do it here. Julia or whatever black box solver you're using. Then this guy is generate a visible line representation from input point tangents. Okay, so this we don't need. We don't use visible line representation. This would just need something to generate the coefficients from the data that we have, so we don't need that. Get parameter start target. This is what specifies the homotopy for start and end. So this we also don't need. So here for this problem is going to be like point to primes. And we don't have tangents for this problem. We only have, right, so we don't need this. Points. Also points to internal representation. Whatever Hoggy's code is using. Then you have this. This is just invert. You have to use the K matrix, so just have to invert intrinsics. You don't need tangents. You just have points to primes. You don't have tangents. That's what you have. Right? Let's come back here. You have just point to primes. You don't have this ID. Right? So then you go to the IO as well. So instead of point tangents to primes, just do point to primes. Here's point to primes image. You remove whatever tangents it is because you don't have tangents to views. Or this guy, just remove the tangents, point to tangent, remove it. Right. Okay. So we have to also this is another to do, right? You don't need lines to primes. I'll just leave it as a stub, okay? Right, so we already touched all of these guys. Point to primes image, remove the tangents, don't use that. So we have no tangents here. That's it. Next, now you have the high level solver interface, which is the end user, whatever the end user is gonna have. So you have some default data, which is like the start solutions. So it's in this header. So we don't have it yet. Just copy from Chicago. It's gonna be called this guy. Default data. So we just copy for that. Same for HXX. Okay. Next, you edit each of them and change Chicago for that guy again. Just doing step by step so we know what it's doing. Right, so this is what we have. There's some data here that we're not going to use, just tangents. So you also have to remove these. Something to do. Next, if you go to the HXX, which is the implementation header, so which also change it. You see you have all these guys, like some ground truth for testing and some start solutions, default start solutions. Then we go here to, okay, let's say you have this guy, default data. How do we get that? How do we, so we have, yeah, this is the, right, so we don't have any other include here. That's the only one. Okay, so let's backtrack a little bit. So you're here, okay. We saw that there's a data, and then in the end, we have this guy, default data. We have the HXX, so you have to fill these guys, okay. I'm in the HXX, so just print inside Julia or whatever other black box solver you have, Bertini, whatever, just print the start solutions, make sure to use a lot of the digits, and copy and paste here. That's your hard-coded default start solutions. Then you have start solutions, but you have some other test functions. Let's start the homotopy parameters for testing. You don't really need that unless you're going to test it extensively. So these are some internals. So here I have some ground truth points. So this is 3 points per view. So of course you're going to have, we can remove this guy, add two more points. This is just copy from my synthetic data set. So 2 more points. Now you have, right. So this is just read this. It will tell you how to get these data sets. And here's the same thing. You have to see what it is. We have the ground truth cameras for these views. You can remove one of them. You can just keep these 2 ground truth cameras. Then you have the tangents, which we don't use for this problem. Then you have tangent, ground truth tangent, which is that. This is the ground truth K matrix.